Let's move on to the next one. So this is an assignment for you to watch this video. Make sure you do that for more details. But in terms of the big picture, your architecture is still encoder decoder. You encode your entire sentence in a single vector, and your decoder is going to consume that single vector as a representation of the entire input sentence. So there is no attention here. We removed attention just to appreciate it. So there is no attention. There's a trick here that I want you to learn. When you're outputting a lot of classes in the end, especially when it comes to translation, language modeling, or word representation, you have as many classes as you have words in your dictionary. This is a good trick to know about. From the last hidden layer of your neural network, you are going to project down to a lower dimension. In this case, you are going from 1000 dimension to 500 dimension. And then from 500 dimension, you go back to a million. It's much better than going from dimension 1000 to a million. So you're saving a lot of parameters and computation at the same time. So that's a good trick to know about. And it's very similar to dimensionality reduction. But that's not the purpose here. Here, you want to take a classical statistical machine translation framework like Moses. So if you're interested in the code for it, just click on that GitHub page. But it's classical. It has nothing to do with deep learning. You want to beat that baseline, and you want to use RNNs. You want to use neural machine translation to improve your statistical machine translation. What can you do? For that, let's recap a little bit about statistical machine translation in general. The task of translation is given an input sentence, English, what is the probability of a French sentence? You want to model that. You can use the Bayes rule. This is going to give you the probability of, if I give you a French, give me the corresponding translation. And then here is where a language model is going to come in. So you want those French sentences to be likely, or to have a high likelihood. This is where the language model is coming. But in the end of the day, this is just a joint distribution between your input sentence and output sentence. This is a joint distribution divided by the distribution of the English, which is going to be your language model for English. If you take a log of that, and then you want to write a model for this log of that probability, the portion that was coming from joint distribution, you can just concatenate your English and French sentences and then featureize them, turn them into vectors jointly. And this is where feature engineering, a lot of feature engineering goes in there in a classical statistical machine translation algorithm. But once you do the hard work of feature engineering, maybe look at your bag of words, maybe histogram of your bag of words, these sorts of feature engineering techniques, or look at the co-occurrence matrix of these English and French, or the words in your English and French sentences, and then do PCA on that. These are going to give you some classical feature engineered features. Once that is done, the rest of it is just linear regression. You're just trying to find the coefficients in front of your variables, and that you can do. And then you might worry about this Z of E, and that's coming out of you having to divide by the probability of the input sentence, which is English, because of the Bayes rule. Or this is actually 1 over something. That's why this negative is going and turning into a Z here. But anyways, that's what you get. When it comes to optimization, you're going to be optimizing over these W's. So this Z doesn't really matter. And then that's going to give you Moses, the algorithm that you see here. What is the idea? Previously, our idea was, let's call Moses on an English sentence. It's going to give us 1000 candidate translations, and then rescore them according to our neural network scores. Here, the idea is a little bit different. The scores that are coming out of your neural network translation, you're just going to use them as features, as additional features to the ones that you were using previously. So this is how you're improving the performance. And basically, many of these wrong details in your translation system in Moses are going to go away because of these additional features. And somebody might say, are these features actually independent of these other features? Maybe they're just a linear combination of those columns in your data. And the answer is no, they are actually independent. If they were dependent, you would see a line here, highly correlated, but these are not correlated. These are the scores coming out of your neural network. These are the scores coming out of your statistical machine translation. So you are actually adding some new information. You are looking at the same problem through two different lenses, through two different perspectives. For more details, make sure that you watch that video. So far, what we have done is trying to improve existing statistical machine learning techniques using deep neural networks, because neural networks were not able to stand on their own at that time and be the state of the art. So you're just using them to help previous techniques. Later on, we are going to get more and more independence from the baseline, and then we are going to stop using the baseline. I think it's a good time for me to stop. For those of you who have questions, I'll be around. For those of you who want to leave, you can leave.